Hello students, in this video I want to talk a little bit about the math behind the physics that we're working on. So we're in the textbook and we're looking at notation, and I wanted to just read this with you because this sounds so complicated, but it's very simple. So a lot of times we're measuring things over time. And so we set an experiment into motion, and then we use time as a measurement of how fast it happens. And in the case of motion, for example, we could change like the angle of a ramp in a classroom, and that would be a factor, and then measure the time it took, for example, a car to go down that ramp. So there's different ways to use time. So here's what it says. Taking the initial time to be 0 as if time is measured with a stopwatch is a great simplification. So since the elapsed time is delta t, this basically just means change in time. The change in time equals the time at the final position minus the time at the 0 position. So if you started a stopwatch at 0, the t sub 0 is 0. And so if you subtract from the final time the initial time, and it's 0, it's whatever t sub f is minus 0, therefore the change in time is t sub f. Okay? And so you see how then we go on and they go on to describe that t or x time sub 0 is the initial position, or v sub 0 is the initial velocity. And so these are just all times that would start with 0, and then it simplifies the equation. So when you're reading this, really take the time to appreciate and say it out loud to yourself what they're trying to impart, because that's the magic. Reading the letters and thinking about what they mean in physics. It's not like we're doing math here, we're really doing word problems. Okay, so now looking at the equation for acceleration, I want you to do the same thing here. If you just kind of breeze through the reading and you just look at this equation, but you're not saying it to yourself, then that is a problem. So let's take this expression right here. This is basically saying that your average velocity equals, and these are velocities at different times, different samples, 30 kilometers per hour plus 60 kilometers per hour divided by 2 equals something by kilometers by hour. Okay, so firstly, we're in the same units, so we don't have to do anything to the units, and there's no units down here. 2 is the number here because we have 2 samples. So we're just taking a simple average, but we've added these units, which makes it look so much more complicated. But really what it is 30 plus 60 equals 90 divided by 2 is 45, and then carry the units over. That makes sense. Okay, so now we're looking at a graph, and so when you do your labs, you'll have to make graphs, but take a look. This is so simple, okay? So we're just looking at the displacement, a measurement of distance. You can tell by the unit what you're measuring, meters, by average velocity, meters per second, okay? And so what I want you to understand here is that here we have that time variable on the x-axis, okay? It's often on the x-axis. And then you're seeing how far something traveled over time, okay? And so then you have these dots, right? So if you're collecting data over time, like that might be per 5 minutes, it might be per 5 seconds. It all depends on what you're measuring. Notice on the graph as well that there are labels on the axes. I would expect you to do that for your lab. And then this seems a bit redundant, but you need a title for the graph. It says the same thing as the axes say. And then having a figure caption. What does this say? So in the case of our lab reports, this kind of information right here would be in the results, the written part of the results. Okay, now as you go along in your reading, you'll see these example problems. And again, I encourage you to actually take out a piece of paper and a pencil and write this down. So if you are in a test and you are reading this question, on dry concrete, a car can decelerate at a rate of 7 meters per second. I would write that down, right? This is a piece of information you have. And then, whereas wet concrete can decelerate at only 5 meters per second squared. So then, now you have two numbers. Find the distance necessary to stop a car moving at 30 meters per second, A on dry concrete and B on wet concrete. Repeat both calculations, finding the displacement for the point where the driver sees the traffic light turn red, taking into account his reaction time of 0.5 seconds to get his foot on the brake. Okay, so this is a basic algebraic equation. I can tell that already. So the strategy here is to draw a sketch. Okay, so you know that the vehicle, go up here, sorry. You know that the vehicle is moving at 30 meters per second, right? So that's time 0, velocity 0. But then you know that the goal here of this question is to figure out how long it takes for it to stop. So you have the velocity sub final equals 0 meters per second. You can gather all that information from the question. And then you were also given these numbers, which you already wrote down. So see how by drawing this line, you give yourself a visual of what those words mean, okay? And then you have a bunch of equations that you've hopefully already written down, but you can look in the textbook while you're working on the quiz, for example. And so now, solution for A. Here's the expert strategy. So if you go through the expert strategy and you just simply write it down, that will help you to understand it. So we already identified the knowns and what we want to solve for. And this in words is just what I already said, that the initial velocity is 30 meters per second, the final velocity is 0, the acceleration is negative 7 meters per second squared, and it's negative because it's moving in a direction opposite to the velocity, and we take x sub 0 to be 0. So now we're looking for the displacement. So what we want to know is the displacement. That's the variable that we're going to solve for, and that is denoted by x here. So this equation is best because it includes only one unknown. So we've isolated that. We know that the values for the other variables are known because we've already taken notes on them up here, okay? And so then you want to rearrange this equation. You can plug numbers into V, you can plug numbers here. Acceleration, you can plug numbers into that. You cannot plug numbers into these zeros, so you've got to try to isolate them, and these are just basic math rules. So to isolate this integer, you have to do, or this expression, you have to do what's happening on this side of the equation to the other side of the equation. And so we have v squared over here on the left side equals v sub 0 squared plus 2a times x minus x sub 0. Okay, so the first thing is we'll do the addition. So if we want to subtract v sub 0 squared from the right side of the equation, we'd have to minus it from this side, so we have to minus it from that side. Okay, so we're going to have this equation here, v squared minus v sub 0 squared over here. Now, to get rid of 2a over here multiplying against this expression, we'd have to divide this expression by 2a, so we'd have to divide this side by 2a as well. And then here we have isolated, we just flip the sides. So now we did our subtraction and we did our division, and now we have x minus x sub 0 equals everything else. And we can plug numbers into everything else because we already figured that out. So we enter the known values, okay? And we know that x sub 0 is 0 because the goal, remember, was for the vehicle to stop, okay? So we're going to go over here, and now we can isolate x. We can do this math. 0 minus 30 squared divided by 2 times negative 7, and we arrive at 64.3 meters on dry concrete. And then we can do the same thing with negative 5 meters per second over here and arrive at 90 meters on wet concrete. And then the last thing is to ask yourself if that makes sense, okay? So remember, in the question, did it seem that a car could stop faster on dry or wet concrete? Let's go see if we had some information about that. Okay, well, in the first sentence, we learned that on dry concrete, the car can decelerate at a faster rate than on wet concrete. Okay, and so we already have information in the question that validates this number, that this number should be smaller than this number, okay? Because it decelerates faster, so the stopping distance should be less. Does that make sense? If you have enough time when you're working out math questions, that's the last thing to ask yourself and to validate. And then you can do the equation backwards to figure out if you've got it right. So now you have 64.3 and you have 90. And you could go back to that original equation you were given and you could plug these values in here and see if they equal the v squared that you already know exists from the information given in the question. All right, I hope this was helpful, and let me know if you have questions.